Hello, so welcome to this section on entropy. Let's first define a random variable x which has some sort of alphabets or outcomes. The outcomes or alphabets of x is denoted as fancy x as such, which is a set of values x1, x2 up to xn. That being said, this means that x is a discrete random variable. Of course, the entropy could be defined for a continuous random variable, but for sake of simplicity, we're only going to be discussing the discrete case. Now, for every discrete random variable, there's a certain probability mass function assigned to it, which is denoted as p of x, which is actually the probability that your random variable will take the value x. With that being said, let's denote all pxk's is equal to pk. So this means that we're assigning to each outcome a certain probability, p1, 2, down till pn, right? So really you can define a random variable x as pairs of outcomes with probabilities. x1 p1, x2 p2, and so on, right? So xn. So those are the alphabets. Those are the probabilities. So this is all we need for defining what a probability mass function and alphabets are. So that being said, now we can define what an entropy is. Given a random variable, discrete in this case, since we have a random variable x, means we have a certain PMF tied to it, denoted by p of x, which we already said is the probability that your random variable takes the value x. So the entropy is denoted as h of x, which means the entropy of random variable x. It is nothing other than the summation of p of x log 1 over p of x, right? Where x spans all the outcomes or alphabets. So a small example on that would be, assume we have a Bernoulli random variable with a probability of success denoted as p. P is the probability of success. This means that the probability that x is equal to 1 is p, and probability that x is 0 is 1 minus p. And here x is my Bernoulli random variable. So we have completely defined our random variable. We know how the PMF looks like. So this is p of 1 and this is p of 0, right? And let's compute entropy of x, which is h of x, right? So by definition, it's the sum, where x is in the alphabet, x log 1 over p of x, right? And the alphabet in our case is only the set 0, 1, which is p of 0 log 1 over p of 0 plus p of 1. Now let's replace the probabilities that we have, which are p and 1 minus p, right? So we get p log 1 over p plus 1 minus p log. So from this simple example, we can really understand what's going on right here. So entropy, in our case, for this random variable, is following expression. So that being said, let's plot h as a function of p and see what's going on. So this is p, the probability of success, and this is h of x. So for p equal to 0 and p is equal to 1, we get h of x. So h of x should be, of course, it's a function of p. And in some references, you would see that for this particular random variable, this is denoted as h of p, because p is the only parameter that x depends on. So to generate x, you only need to know p. To write code or to perform a certain experiment to generate a random variable x, you only need to know p. Therefore, it is correct to say h is a function of p, right? So we replace x by p. So for p is equal to 0, you get the 0 log 0 here and the 1 log 1 here. So a log 1 is 0, and 0 log 0 is not defined, but the limit is 0, right? So you get at p is equal to 0, you will be over here. And at p is equal to 1, we have the same argument. So at p is equal to 0 and at p is equal to 1, the entropy is 0. And if you would plot that, you'd get a maximum on p is equal to half. If log is defined to the base 2, then you can see that you would get an entropy of 1, right, for p is equal to half. And the rest would look like this, something like this, right? So I'm not really concerned with the form right now, just concerned in how this function behaves, how the entropy behaves as a function of p. It's really nice and really easy to understand what's going on. So walk with me here. If p is 0 or 1, what does that mean? It means that you no longer have a random variable. You can predict the outcome. So for p is equal to 0, it means that probability that x is equal to 0 is 1 minus 0 is 1. Or alternatively, probability that x is equal to 1 is 0. That's it. This means that x is equal to 1 will never happen. Alternatively, this also means that x is equal to 0 is going to happen for sure. So we don't have any uncertainty. Similarly, for p is equal to 1, probability x is equal to 0 is 1 minus 1 is 0, and probability that x is equal to 1 is 1. Which means that 1 is going to happen all the time. So the keyword here is uncertainty. So here we have no uncertainty. We know exactly how x is going to behave. Right? And that is why your entropy is 0. When the entropy is 0 or close to 0, it's telling you that there is no uncertainty. You are certain of what x is going to behave like, what the outcome of x is going to be. On the other hand, when h of x is maximum, means it's maximum given a certain PMF, given a certain random variable. This means that you have maximum uncertainty. You have maximum chaos. You don't know how the system is going to behave. This is the most uncertain way the random variable is going to behave. And in our case, it's when p is equal to half for a Bernoulli random variable. So again, when p is half, it's when we have most uncertain. We don't know which outcome is more likely to happen. Now, when you go towards p is equal to 1 or p is equal to 0, you could see that the uncertainty is decreasing. Right? And it's decreasing in this type of behavior, in a log difference behavior or log sum behavior, which is the entropy. So yeah, this is the intuition behind entropy. It's easy to see it when we're studying a Bernoulli random variable. And one more thing to shed light on is that the entropy is measured in bits. Log is to base. So if the base of the logarithm is base is 2, then the units is bits. And we'll say why. Whereas if the base is the exponential, that means the log becomes the ln function, then normally people refer to the unit as nat. Now this is applied basically to telecommunications, computer science, and so on. It is worthy to note that entropy also shows in many other domains, such as thermodynamics. And it's usually a measure of uncertainty or chaos of a certain system. When we're in thermodynamics, we won't measure entropy in bits or nat or whatsoever. No, it's usually measured in joules. Let's restrict our study to base 2. So the unit is bits. Okay. So now, why is h of x measured in bits? Why bits? So why is this function, which is a function of probability mass function, measured in bits when the log is of base 2. So it's worth noting that the entropy is the average length of the shortest description of a random variable. And what does that mean? It means it is the average number of questions you need to ask to model your random variable to arrive at the right solution. Right? So let me give a small example on that. And let's name this example why bits or questions. Why questions? Why does it measure the number of questions or number of bits that one needs to arrive at the right solution? Assume that I have the following PDF or the following distribution. X comes from the following outcomes A, B, C, D, so it takes only 4 distinct values, and the probability of each of the following outcomes is given as follows. So P of X is equal to half if X is equal to A, 1 over 4 if x is equal to b, and 1 over 8 if x is equal to c or x is equal to d. So this is our random variable right here, completely defined. So immediately we could compute the entropy, which is the sum over all possible values of x, a, b, c, and d, p of x log to the base 2 of 1 over p of x. So let's replace all the values of x, which is p of a log 1 over p of a plus p of b. Now let's replace the values. I'll get half log 2 plus a quarter log 4 plus eighth log 8, and again eighth log 8, right? So you can compute this on a calculator, or you can compute it really quick because this is log 2, right? Log 2 is 1, log 4 is 2, and log 8 is 3. So after you do the math, you end up with 7 over 4, or 1.75 bits. What does that mean? So if I want to compute the average number of questions one needs to arrive at the correct solution, I first have to model what questions I need to ask, right? So let's start asking if x is equal to a. So I'll draw some sort of tree right here. Is x equal to a? If yes, I'm done. And if no, I need to ask another question. Is x equal to b? If yes, I'm done. And if not, I need to ask a third question. Is x equal to c? If yes, I'm done, and if not, then x is definitely going to be d. So here at most I asked how many questions? I asked 1, 2, and 3. 3 questions. 3 question marks. So at most I asked 3 questions. Now what is the average number of questions? Average number of questions, right? So what is the probability that x is equal to a times the number of questions when x is a plus b times, so this Diaz or hashtag symbol is the number of questions I need to arrive at b or a, plus probability that x is c times the number of questions I need to arrive at c, plus probability x is d times the number of questions I need to arrive at d. We know the probabilities, which is half, 1 over 4, 1 over 8, and the same for d is also 1 over 8. Now, what is the number of questions I need to arrive at a? We only asked one question. Is x is equal to a? If yes, then I asked only one question, right? Now, what is the number of questions I need to arrive at b? If x is truly equal to b, then we start. Is x is equal to a? No, that's one question. Is x equal to b? Yes, so it's 2 questions. What is the number of questions I need to arrive at c? You could see that it's 3 questions. And similarly, x is equal to d is also 3 questions. So if you compute that, you're going to end up with the entropy. And it's easy to see, those are your p of x's right here. If we compute the entropy, we have our p's over here, which are also over here. So this is 1, this is 1, this is 2, and those 2's are 3, right? So 1, 2, 3, 3. And you can see that the average number of questions in this case is exactly equal to the entropy. We will see later on that the lower bound of the entropy and entropy plus 1 is the average number of questions. So the average number of questions needed to arrive at the correct solution is bounded between h of x and h of x plus 1. It is crucial to note that the entropy does not give you a method or a way to ask the right questions. No, it tells you that you could model your random variable as number of questions bounded between entropy and entropy plus 1, but it does not tell you what method you need to do. Now here we picked the method, right? I could have picked another method by starting with d, and of course everything would be different. The average number of questions would be different. Everything will be different. And we would end up with average number of questions higher than 7 over 4. So if I started with D, then C, then B, then A, then 3 is here, and 2 is here, and 1 is here. You could see that this is maximized, right? You're flipping everything around. So the outcome that is most likely to happen, you start asking it first. This is a way to reach the entropy in our case. Notice that if I change here the probabilities for C and D, you would not reach exactly the number of questions. You would be bounded between h of x and h of x plus 1. Try to do this example when try solving the average number of questions using this tree method for, I don't know, for x is equal to c. Let's say the probability is 1 over 8 minus 1 over 32. And here 1 over 8 plus 1 over 32, right? So try answering this and check if it's still bounded between h of x and h of x plus 1, okay? So now we saw why the entropy gives us an idea of the average number of questions needed to reach the solution, right? Now, if we didn't model it that way, if we modeled it another way, so let's say you started asking if it's D, then downwards, as we said, the average number of questions will increase. So you're asking more questions than you should, right? Now, this is questions. Now, why bits? So we all know that questions could be modeled as bits in computer science or communications, right? So here, if I need one question to model x is equal to a, why not encode or model x is equal to a as 1 bit? I don't know, call it 0. and x is equal to b, model it as 2 bits, 0, 1, let's say. X is equal to c, model it as 3 bits, 0, 0, 1, and x is equal to d, also 3 bits, 0, 1, 0. So as you can see, the bits is equal to the number of questions that we're asking. So 1, 2, 3, 3. You can see 1 bit, 2 bits, 3 bits, 3 bits. But of course, they should be distinct, right? They're the same. That means you're modeling the same, outcome. You're saying that C and D are the same, where they're not. Okay, so what is the average number of bits? Again, 1 bit times the probability that x is A, which is half, plus 2 bits times the probability that x is B, which is 1 over 4, plus 3 times 1 over 8, again, plus 3 times 1 over 8, and you would get, again, the entropy, which is bits. And that's why it's bits. So really, bits and number of questions to arrive at the correct solution should be understood as the same. Now, if we didn't model it that way, if we modeled it the naive way without acknowledging that x is a random variable, then we do this, right? So x is A, why not model it? Since we have 4 outcomes, then 4 is 2 square. Square means you need 2 bits to model all your outcomes. So 0, 0, 0, 1, 1, 0, and 1, 1, right? So here, what is the average number of bits? It's obviously 2, which is more than 1.75. Now, I know some of you are going to say, oh, but there's no such thing as 1.75 bits. It's either 1 bit or 2 bit. I know. But when the number of outcomes increase, like when you're talking about 64 outcomes or 128 outcomes, this is going to make a big difference. When we're talking with 40 outcomes, here you're going to have times 10, times 10, you could save 3 bits. And you know what 3 bits means in the communication world. When you're saving bits for transmission, you have more data rate. You're increasing your data rate, right? You're sending less information in less time. So in this slide, we talked about why the entropy in our case is measured in bits or questions. Now, let's state some useful properties. So this was the definition of the entropy. The first property, prop 1, h of x is a non-negative value. And why is that? This is easy to prove. Well, all your p of x's are positives, so this part is positive, right? Or equal to 0 at the minimum. Why is log 1 over px also positive, so that we could say that the sum of positives is positive and then we're done? Because p of x is between 0 and 1. That means 1 over p of x is at least 1, right? So log of 1 over p of x is greater than log 1, which is 0. So also log 1 over p of x is positive, which means that this thing is positive and this thing is positive. So the sum of positives is also positive. And the proof is done. Now, another property is the change of bases. So let's say I don't want my entropy to be of base 2. I want a more generic basis. If my entropy h subscript a of x represents the entropy where the log is of base a, then what is the relation between HA of x and HB of x? Log B of 1 over P of x. So we all know that log B of x is log B of A times log A of x, right? This is the constant. So using this property, you can go from HB of x to HA of x as follows. So it's the sum of P of x. Now let's use this property in blue. So instead of log B 1 over P of x, I'm going to write log B A of A times log A of 1 over P of x. This thing is a constant, so it goes out of the sum. Therefore, we end up with log BA times sum of P times log A 1 over P, which is HA of x, right? So HA of x. So to go from one base to another, as you go from logarithms from one base to another, you could also go from entropies from one base to another using the same scaling constant, log BA, right? So this is property 2. And one more property, which is not really a property, it's just rewriting the entropy. So notice that h of x is sum of just flipping the log and the p, right? So log 1 over p of x times p of x. And what does that mean? It means it is the expectation over p of x of the function or the random variable log 1 over p uppercase x. So since you're averaging this function, we're multiplying each value of this function by its corresponding probability, which means we're averaging this function. So that's it for this lecture. We saw why the entropy is measured in bits or number of questions. We gave an example on that. That's after we introduced what the entropy is and giving a really small example on the Bernoulli case. Then we stated those three properties on the entropy, which is the non-negativeness of the entropy, property 1, and the change of base of the entropy, property 2, and that the entropy is the average of log 1 over the PMF. That's it for this one. I'll see you in the next one.